Have you ever faced challenges where somebody had to design a product feature that you were relying on, and you got that, and you found that there are so many bugs here that it can't really work, or that it seems to work fine, but then it doesn't stand the test of time? As an engineer, when you want to design a new product feature, how should you go about the process to make sure that it'll stand the test of time and it is eventually of a high end of quality? Well, so I have a method that I call the SMPT method, which is spec, mock, prototype, and test. And you can use this to design robust engineering features in your products. So spec is essentially getting the specification of your product, making sure that you have all the requirements before you ever start developing anything. After that, you should mock this or simulate this before you design a prototype. So have a rough idea, do simulations in whatever software or whatever system you can use to know that this idea is going to work. And you could use multiple of these. Then you should create a prototype, which is going to be a functional system that meets the specification and is going to give you the desired output. And then you go ahead and test. And once you have done this test, maybe you'll have bugs. You will then have to repeat the whole SMPT process. And when you're satisfied, you can eventually go ahead and launch this product. So I want to take a few examples of how we have done this in the past. So in Perchol, there was one time we were working with a client for an autonomous driving project. And the target was that we wanted to make sure that the car, when it made right turns, it was usually making very sharp turns, and we wanted to make those smoother. So to do that, if we talk about this process, the way we did that was, first, I took the spec, right? So in this case, I had a client. So I tried to understand the whole process from them. I got the specifications. But usually what happens is sometimes the person who is dealing with the system doesn't necessarily think about it from a perspective of a third party, right? Because they're so deep into the process, a lot of those things are obvious to them. So one of the first things I did was I made sure that I understood this. I documented everything in detail. And once I understood what we had available, what kind of requirements we have from the process, I then went ahead and wrote that down into a document and got an approval from the project manager that this is indeed what we were looking for. The next stage was to mock this. And the way I like to do this whenever it involves algorithms is to use some sort of a scripting language. Mostly I use MATLAB or Python, but depending upon your field, your domain, you might have familiarity with different languages like R or any other language, and you can use that to determine what makes the most sense for you. So with that, first of all, I created a Python simulation, which gave me an idea of exactly what the path stitching algorithm would look like. And of course, I did a lot of math beforehand, implemented that in Python, created a bunch of plots, and this is not at all plugged in the vehicle, right? I'm just looking at, will this logic make sense if I assume certain inputs? And once I was confident that yes, it indeed did make sense, I then went ahead and said, okay, let's now convert this Python code into C++ and plug it into the actual software. So at that point, I know that the algorithm works. I trust by doing a lot of simulation and test cases that this is going to indeed give me the desired results for a variety of inputs. And then I convert it into C++ code, which then can be put onto the vehicle. So this, we have already talked about the spec stage, the mock stage with Python, the prototyping stage in C++, and then eventually it's put on the vehicle and we do some tests. And based on the tests, if the results that come in are in line with what we expect, then it can be launched. And if it's not, then it can't be launched. And eventually we launch this product. And then another example in the field of robotics is that what I've done in the past is, in this case, I'm talking about a specification that doesn't directly come from the customer, but it comes from me. So there was a robot for which I had deployed a motion controller. And what I used to do was, there was the control, any controller has the objective of meeting a specific target. So imagine that you are standing at a position and you want the robot to go to a different position. So you'll give it a new target. And it looks at the difference between these and says, okay, I have this much error. So to minimize that error, I'm going to take some action. And usually it'll operate a motor. But what happens is, if you just give it a command that you have to cover, say, 100 meters, then it's going to immediately try to give all the current to achieve that as quickly as possible. So we put in some constraints. And And what I had observed is that even though the robot was doing the motion that I intended it to do, when it tried to settle, the settling was very slow. So there was like a tail to the settling if I made a plot between velocity and time. So what I understood is that I need a new product feature. This product feature didn't explicitly come from an external customer, but it came internally from within my team. And once I understood that, okay, this is the problem. So I documented all the cases. I looked at why it would be important for us to change this. What would be the advantage of using a better process? And then from that, I spec'd out that I would need a trajectory generator. Now, there could be multiple orders of trajectory generator, but we decided on a specific type of trajectory generator, which I'm not going to go into the details of. But eventually, once it was done, then the next stage was mocking. So in mocking, I used MATLAB. And in MATLAB, what I did was I considered all possible edge cases. So I thought about, okay, what happens if my robot has to go from point A to point B, but I start from, a point B is behind point A, or it's in front of point A. If the initial velocity is in negative direction, positive direction, if my constraints are unrealistic, maybe I have seized such, I put an acceleration limit of 0, and I'm expecting that the vehicle should start from a position and go to another position. Obviously, my system should give me an error and say, hey, I can't compute this trajectory. So I came up with like 60 or odd test cases, and I did all of them in MATLAB. I generated plots for each one of these and made sure that all of them were covered. And when I was satisfied that all of this actually meets my expectations, after that point, I said, okay, now let's go ahead and deploy this whole system in the actual robot, which was using embedded C++. So for that, I then eventually said, okay, let's do this. But then after the deployment part, when the prototype was ready, for testing, in my code itself, I had a lot of logging variables, which would give me the data back. And I could compare that the inputs were actually giving me the sort of outputs that I expect. So in this case, again, we have this SMPT method, which could be deployed and which gave us the desired results. So both of these examples that I've given so far are both related to software. But it doesn't mean that that's the only place where this approach is valid. You could very well use this for hardware. So as an example, Statcon Electronics and Statcon Powtech are primarily power electronics based companies. And so we do a lot of this methodology or processing in our approach here. So let's take an example of hardware, right? So for example, we're currently working on designing an improved front-end converter for our devices. So to do this, first of all, we looked at our current products and we saw, okay, where can this product be useful? And then based on that, we looked at its performance, we saw the gap, and then we realized, okay, an improved front-end converter should have this particular specification. Once that specification was drafted, we then went ahead and said, let's look at how we can mock this. So to mock, in case of electrical systems, we typically first start by designing a schematic system, which is then simulated using LT-Spice. If it's power related, you could use PowerSim. And then once we have those, sometimes we also use MATLAB and Simulink. So once you've done all the analysis, you might have to mock certain parameters. You might have to say, okay, I expect my system is going to have an input supply, and this is the fluctuation in the supply. I'm going to add certain ripples. I want to add certain noises, and all of those functionalities you could do in simulation softwares like Simulink and LT-Spice or various kind of simulation softwares. So once we've done that and we're satisfied that this logic works, then we would get ahead into the prototyping stage. And even in the prototyping stage, you don't necessarily need to have the entire hardware. You could definitely have hardware with some simulation packages in the loop. And then you can iterate on to the stage where you eventually make the prototype. Because hardware is a slow field and it takes time to order a component. And I wouldn't want to have like an entire PCB ready when I could just use a microcontroller and give some signals to be able to basically test my idea. And after that, obviously, we then go ahead and do the testing. And then based on the testing, if the SMPT cycle has worked for us, we would go ahead and do a launch. Similarly, for hardware, in mechanical systems, at Statcon Powtech, we always try to optimize our assembly lines. We try to improve the amount of time it takes for us to deliver a product to the customer, obviously while making sure that the product quality is extremely high. So what we did was we did a time motion study, And based on that, we understood that certain procedures in our production team or on the manufacturing shop floor were taking a lot of time. And to minimize that time, we thought about how can we make sure that the motion of a particular production worker goes down. So to do that, we basically, again, we started with the specification. We had an entire document with listed out the steps, and we thought about what can we do to optimize this process, and we spec'd out different ideas. And then we did this mock. Now, in this case, we had to basically make a system which would try to collect all of their relevant tools together. So the time that it takes for them to go from station to station goes down, and they can have all the pieces together in one place. So here, for mocking, we basically took a cardboard box, right? It didn't matter. We didn't have to go and design complicated things in CAD, do 3D printing or anything else. Just a simple mock-up idea. We mocked up something with cardboard, talked to the production workers, gave them this cardboard version, and saw how they felt about it. And once the feedback was positive, then we said, okay, let's go ahead and make a metal sheet version of this. Let's try to create a proper CAD model, and then we could create something for internal use. Again, so we did that prototype, and then once that prototype was successful, we monitored it for a few days. We said, fine, now we can go ahead and after a successful test, we can launch it. Now, one very important thing when it comes to the test component of this is that you don't need to just test that feature which you've developed, but you actually need to look at the entire gamut of features that you have. Because imagine if you create one feature and that feature works fine, but it actually makes a bunch of other features in your product fail, then it's not a really useful feature. So as an example, I remember that recently at StatCon PowTech, we made some changes in our system so as to have improved communication with the lithium battery. So the system was initially designed for communicating with, the solar inverter was designed to communicate with lead acid batteries, and it works with lithium batteries as well. But then we made some improvements as the battery management systems improve in the market. We make sure that our products are compliant and ahead of the curve. So we made some changes there as well. But then once we made those changes, we weren't just making sure that it works with lithium batteries. We wanted to make sure that, okay, if I go ahead and test this with lead acid batteries, if I go ahead and test a variety of input features, not just the ones that my customer is looking for right now, all of those have to work properly. And this is really what you need to do anytime you're changing any feature in your product. I know it's cumbersome, but you have to make sure that all of the features work as expected, because, it's not useful if you say, well, I fixed the tire, but then in return, I broke your suspension. Nobody cares about a car like that. So that part is really important. And you can automate those processes if in your software you have unit tests. You have a continuous integration, continuous deployment, which makes sure that anytime you create a product, you're able to or make a change in your code, you're able to make sure that you're testing all the features. For electrical systems, you have a test jig, which can go in and test all of your points in the circuit by giving them different inputs and make sure that the whole thing works. So before shipping out any product, before shipping out any feature, you have to make sure that everything works throughout. Now, one final note I want to add is that, now this process sounds like very well, rosy, hopefully we'll give you all the results. Then why do people, it seems pretty obvious, right? Why do people not do this? And I've observed that what happens is, even with experienced engineers, they will typically they would not go into speccing in a lot of detail. They might miss a lot of steps when it comes to speccing. And they would get an idea, they'd be like, okay, yeah, I think it makes sense, we'll go ahead and make that feature. And then they wouldn't write everything down in detail. They might write it at a very high level, and then eventually, when you go ahead and deploy it, you'll see that many of the features are missing. And so that's the first problem. The second problem that I've seen the most is that people absolutely miss the mocking part, right? They would not simulate at all. Especially if you're more senior, you feel like, I don't need to do this. I'm pretty confident. I understand how to design these features. I've done many of them. And then you don't mock. You go ahead and prototype. You spend time, you spend money, and eventually you have a product or a prototype which is costly and which hasn't gotten you anywhere. And now you have to go back and look at what went wrong, right? So even though it does take time, it's always better to simulate. But again, with the caution that you can't spend, 6 months trying to simulate something when your customer needs a product in a day. So when you're doing these simulations, make sure that you can make a lot of simplifying assumptions. It's okay to start simulating by assuming an ideal environment. This is what happens a lot in physics, because people assume things like, oh, let's assume that there's a point mass. Let's assume that gravity is uniform everywhere, right? So you can make a lot of simplifying assumptions, see that your idea actually works, and then you can slowly introduce other changes into this once you are able to vet that idea. But it's important to remember that you should not just keep simulating forever. Do a simulation, make sense, make a quick prototype, see that it works, and then keep going. And prototyping also can have multiple stages. You could have simple, smaller versions before you eventually go and deploy the product. So in my case, where I was giving these examples of robotics, if I have to test my trajectory generator, I'm not going to go and integrate the trajectory generator with the entire system when I'm writing the code in C++. First of all, in my C++ code, I would write a piece of code that is just going to test my particular code of trajectory generator, and I would integrate it with a motion controller just to make sure that the motion works as expected. I'm not yet worried about receiving commands from different targets and from different planners and then going ahead and doing things. I'm just concerned about making the two different modules, they are integrated and they work as expected. So that's it. I think that this SMPT model is something that you can use whenever you're developing a feature. Share it with your team and let me know if you have other approaches that you've used that have helped you make better products.